Let's explore the considerations for designing an electrical service for a small strip mall, taking into account the provided information. The design process begins with load estimation. Firstly, let's consider the house panel. A typical residential load is assumed to be 10 kilowatts. Secondly, for the hardware store, which has 2,000 square feet, we can assume a commercial load of 5 watts per square foot. Multiplying 5 watts per square foot by 2,000 square feet gives us 10 kilowatts. Thirdly, the grocery store, which has 4,400 square feet, will require a more detailed calculation. We will get to that shortly. Fourthly, regarding the rooftop unit, which is rated at 7.5 tons, we need to convert tons to kilowatts. Knowing that 1 ton equals 3.5 kilowatts, we multiply 7.5 tons by 3.5 kilowatts per ton, which results in 26.25 kilowatts. Fifthly, concerning the troffers, there are 68 troffers, each with 4 lamps, and each lamp consumes 20 watts. Multiplying 68 troffers by 4 lamps per troffer by 20 watts per lamp gives us 5,440 watts, or 5.44 kilowatts. Now, we have the initial load estimates. The house panel is 10 kilowatts, the hardware store is 10 kilowatts, the rooftop unit is 26.25 kilowatts, and the troffers are 5.44 kilowatts. We still need to calculate the grocery store load. Adding these values, excluding the grocery store, gives us a preliminary total estimated load of 61.69 kilowatts. Let's delve into the grocery store load estimation. Refrigeration load is a significant factor in grocery stores. We will assume 20 watts per square foot for refrigeration. Multiplying 20 watts per square foot by the grocery store's area of 4,400 square feet yields 88 kilowatts. Lighting is another important consideration. We will assume 2 watts per square foot for lighting. Multiplying 2 watts per square foot by 4,400 square feet results in 8.8 kilowatts. Other loads, such as heating, ventilation, and air conditioning or HVAC and electrical equipment, also contribute to the overall load. We will assume 4 watts per square foot for these other loads. Multiplying 4 watts per square foot by 4,400 square feet equals 17.6 kilowatts. Summing up the grocery store load components, we have 88 kilowatts for refrigeration, 8.8 kilowatts for lighting, and 17.6 kilowatts for other loads, giving us a total estimated grocery store load of 114.4 kilowatts. Now, we can calculate the total service load. We have 10 kilowatts for the house panel, 10 kilowatts for the hardware store, 114.4 kilowatts for the grocery store, 26.25 kilowatts for the rooftop unit, and 5.44 kilowatts for the troffers. Adding these values together results in a total service load of 166.9 kilowatts. With the load estimation complete, we can proceed to the service design phase. The voltage is given as 120/208Y, which is provided by the transformer. To determine the amperage, we convert the total load to amps. Since many loads will be single phase, we'll use 120 volts as the base. Dividing 166.9 kilowatts, which is 166,090 watts, by 120 volts gives us approximately 1384 amps. Next, we need to select an appropriate conduit size. The conduit must be large enough to accommodate the required number of conductors and handle the calculated amperage. It's crucial to consult the National Electrical Code, NEC, for specific requirements and tables related to conduit fill and ampacity. A main panel board should be installed with sufficient branch circuits and capacity to handle all the individual loads. This panel board serves as the distribution point for the electrical service. Metering is essential to measure the total electrical usage of the strip mall. A metering system should be provided to accurately monitor consumption. In addition to these core design elements, there are several additional considerations. Firstly, demand factor is a crucial aspect. A demand factor accounts for the diversity in load usage. Not all loads will operate at their maximum simultaneously. Applying a demand factor can reduce the overall service size. Secondly, power factor correction may be necessary. Power factor correction devices can improve power quality if the power factor is low, which can lead to inefficiencies and penalties from the utility company. Thirdly, code compliance is non-negotiable. The entire design must comply with all applicable electrical codes and standards, including the National Electrical Code, NEC, and local regulations. Remember that this design is based on the provided information and assumptions. Actual load estimates and design requirements may vary depending on the specific building details and equipment specifications. Consulting with a licensed electrical engineer is highly recommended for more detailed and accurate design. An electrical engineer can perform detailed load calculations, select appropriate equipment, and ensure compliance with all applicable codes and standards. The NEC provides guidance on various aspects of electrical installations. For example, NEC Table 310.15b16 provides ampacities of insulated conductors rated up to and including 2000 volts based on various insulation types and installation conditions. This table is crucial for selecting the correct conductor size for the calculated amperage. Article 220 of the NEC covers branch circuit, feeder, and service calculations. This article provides detailed methods for calculating the loads of various occupancies and equipment. It includes demand factors for different types of loads, which can significantly impact the overall service size. For example, Section 220.42 provides demand factors for general lighting loads in various occupancies. These demand factors recognize that not all lighting will be on simultaneously, allowing for a reduction in the calculated load. Section 220.53 provides demand factors for household electric ranges and cooking appliances in dwelling units. These demand factors are based on the number of appliances and their rating. Section 430 of the NEC covers motors, motor circuits, and controllers. This article provides detailed requirements for motor protection, conductor sizing, and control circuits. It includes tables for determining the full load current of motors based on their horsepower and voltage. Section 440 of the NEC covers air conditioning and refrigerating equipment. This article provides requirements for the disconnecting means, branch circuit conductors, and overload protection for air conditioning and refrigerating equipment. It includes tables for determining the minimum circuit ampacity and maximum overcurrent protection for these types of equipment. For the hardware store and grocery store, it's important to consider receptacle outlets. Section 220.14 specifies that each receptacle outlet is calculated at not less than 180 volt amps. This is relevant for determining the branch circuit load for receptacles. The lighting calculation should also consider the type of lighting being used. LED lighting is becoming increasingly common due to its energy efficiency. When using LED lighting, the actual wattage of the LED fixture should be used in the calculations. The NEC also addresses voltage drop. Excessive voltage drop can cause equipment to malfunction and can also be a fire hazard. The NEC recommends limiting voltage drop to 3% in feeders and 5% in branch circuits. Proper conductor sizing is essential to minimize voltage drop. The selection of overcurrent protection devices, such as circuit breakers and fuses, is also critical. These devices protect the electrical system from overloads and short circuits. The NEC provides specific requirements for the sizing of overcurrent protection devices based on the ampacity of the conductors and the type of equipment being protected. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, which allows the overcurrent protection device to trip and to energize the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, which minimizes the risk of electric shock. The NEC provides detailed requirements for grounding and bonding. Surge protection is also an important consideration, especially in areas that are prone to lightning strikes. Surge protection devices protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. The NEC provides guidance on the installation of surge protection devices. The location of the electrical service equipment should also be carefully considered. The equipment should be accessible for maintenance and should be protected from physical damage. The NEC specifies minimum working clearances around electrical equipment. The working clearances provide sufficient space for electricians to safely work on the equipment. The design should also consider future expansion. It's often wise to provide extra capacity in the service to accommodate future loads. This can avoid the need for costly upgrades later on. The electrical drawings should be clear and accurate. The drawing should show the location of all electrical equipment, the size and type of conductors, and the overcurrent protection devices. The drawings should also include a load schedule, which lists the loads of all the circuits. A well-designed electrical system is essential for the safe and reliable operation of any building. By carefully considering all of the factors discussed in this narration, the listener can design an electrical service that meets the needs of the small strip mall. Again, consulting with a licensed electrical engineer is important for ensuring a safe and compliant design. The electrical engineer will consider local amendments that are made to the national code, which can sometimes occur and should be followed. They will also be able to use specialized software and engineering practices to arrive at the best outcome for the design. This is critical because electrical design is complex and can have serious ramifications if not completed correctly. Firstly, a mistake in the design can result in a fire or electric shock that can damage equipment or injure people. Secondly, the utility company might not approve the design, which delays operations and will result in fines. Thirdly, the local authorities might not pass the construction, which means that the design needs to be reviewed and corrected and submitted again, resulting in more costs and delays. Electrical engineering is a complex subject and there is always more to learn. Keeping abreast of the latest codes, standards, and technologies is crucial for ensuring the safety and reliability of electrical systems. A proper electrical design considers safety and future use.